This is the last lecture of this unit, and interestingly, it will be the beginning point of higher studies if you opt for masters in similar field. The thing is, if we had a normal parallel plate capacitor, then we could simply say the capacitance will be equal to permittivity of the medium multiplied by cross-sectional area divided by distance between the two plates, which we have already assumed so far. But this is actually not the case. A normal parallel plate capacitor is composed of two metallic plates, but here we have metal on the one side and semiconductor on the other side. Obviously, this will lead to some changes in our analysis. Topics which we are going to study are actually very broad, as the complete theoretical background about what is actually happening may require knowledge of many other topics like Schrodinger's equation, quantum mechanics, etc. But here we will be having a general and very simple discussion. First, consider a normal capacitor in which charges are deposited exactly at the surface, and these charges exert repulsion force on each other. But since all the charges are at surface, the force will be in the y direction. Now consider a MOS capacitor. On the semiconductor side, particularly in depletion and inversion region, charges, since occupying space in x direction also, they exert repulsion force in x direction also, which reduces the charge holding capacity or capacitance of the capacitor. We already know that the region in the x direction, which consists of charges within the semiconductor, is referred as depletion width. For simpler analysis, we will assume there are actually two capacitances. One is oxide capacitance and the other is depletion capacitance. And as can be seen, these two capacitances are in series. So, net capacitance per unit area will be equal to permittivity of the oxide divided by width of the oxide plus permittivity of the oxide divided by permittivity of the semiconductor into depletion width. In this formula, except depletion width, all the other parameters remains constant even if the applied gate voltage is changed. And we also know the depletion width increases until the gate voltage is equal to threshold voltage and then becomes nearly constant. Therefore, we can also find minimum net capacitance value. Our assumption of single capacitance, which we have considered until the last lecture, holds good for DC analysis. But for AC analysis, it may not give satisfactory results. Consider an n-channel MOS capacitor with positive trapped oxide charges near the semiconductor side. We have a graph of capacitance with respect to applied gate voltage, which is found experimentally. The maximum value of capacitance occurs at accumulation region, and the capacitance decreases as the depletion width grows until the gate voltage reaches threshold voltage. We know the formula for flat band voltage. In this formula, we have assumed there is only single capacitance, but this capacitance will not be used for AC analysis. This capacitance will be replaced by flat band capacitance, whose formula is shown on the screen. After inversion is reached, the small signal capacitance depends on whether the measurements are made at high frequency or low frequency, and these high and low frequency are defined with respect to generation recombination rate of the magnetic carriers in the inversion layer. If the gate voltage is changed rapidly, the charge in the inversion layer cannot change in response and thus does not contribute to the small signal AC capacitance. Hence, the semiconductor capacitance is at a minimum, corresponding to maximum depletion width. On the other hand, if the gate voltage is changed slowly, there is time for magnetic carriers to be generated in the bulk, drift across the depletion region to the inversion layer, or go back to the substrate and recombine. In this case, the semiconductor capacitance is very large because the inversion charge increases exponentially with surface potential. Hence, low frequency net series capacitance in strong inversion is basically insulator capacitance once again. The same way we can draw the graph for p-channel MOS capacitor. Few more important and interesting points are written in the short notes which you must go through. Also, this is a very theoretical topic. You should read books also. This is just an introductory lecture of AC analysis. But remember, in examinations, there are very less chances of questions from AC analysis to be coming. So, make sure you are using the formulas as per the condition. For example, In exams, there may not be any need for you to find flat band capacitance for finding flat band voltage. You simply have to find the offset capacitance and assume that we are dealing with DC case and simply put the value of offset capacitance to find the flat band voltage. Our fifth unit, MOS capacitor, is completed here. Next unit is MOSFET. However, you should not go to the next unit unless and until all concepts of this unit are clear to you.